Okay, so where we left off was talking about the fact that the four quantum numbers are really the address of where one could find an electron in an atom. And when I say address, it's like it gets you to the house, but you don't know where in the house it is. In the sense that we can't exactly pinpoint it. Remember, Heisenberg's uncertainty principle says we can only know the probability of where it's going to be. So the four quantum numbers give us the probability of the region it's going to be in. And so the first one, and the N, is the energy level, and that's like the country that it's in. And then the second one, the L, is telling us the subshell that it's in. And then the ML tells us which orbital in that subshell, and then the MS, which spin it has, clockwise or counterclockwise. So at the end of the last video, we wrote out all the addresses, or the four quantum numbers, for all 11 of sodium's electrons. And so it's kind of cool. We can predict where every one of them is. But this is a really rough way of showing where they are. Like, it's okay, because sodium only has 11 electrons. But when we get higher up in the periodic table, you're going to need a lot of pages to write these out. So scientists were like, okay, there has to be a better way. There has to be a better notation that would show the same thing. So the first thing we say is, all right, so electrons with the same value of N, so the same value of N, are in, we say they're in the same shell. So, and then they went on from that. Once they did that, then they said, okay, so if N is equal to 1, we're going to say they're in the K shell. And if N is equal to 2, we're going to say they're in the L shell. And if N is equal to 3, we're going to say they're in the M shell, and it would go on from there. Okay, so now this was back like 1920s, 1930s. There's really only one place nowadays that you'll ever see the N's referred to as K, L's, or M's, and that'll be in nuclear. We'll talk about the K shell a little bit when we come back to nuclear. But originally, when they were trying to figure out how should we do this, they did think of using the, well, and they did name the N equals 1, the K, the N equals 2, the L, the N equals 3, the M, etc. Then they went to the L's. So they said, so these are electrons with the same N. So electrons with the same N and L, so not just the same N, but the same N and L, are in the same subshell. Okay, so inside the shell there are subshells, and so if they have the same N and the same L, they're in the same subshell. And they said, well, when L equals 0, that's the S subshell. And in case you're wondering what the S stands for, it stands for sharp. Okay? Then if they're in the L equals 1, they're in the P subshell. And P stands for principal. If they're in the L equals 2, then they're in SP, say it with me, D subshell. And the D stands for diffuse. So in case you ever wondered, where do these SPDFs come from? So the KLM, they're in order. But the SPDF, they are names, and I think they're probably from the lines in the spectra. I'm kind of making that up, but I think I might remember it. And then the L equals 3 is the F subshell, and F stands for fundamental. And then L equals 4 would be the G subshell. And it was at F that they said, okay, wait, like we can't go through the 26 letters of the alphabet in random order. And so after F, they decided, let's go in order. So G stands for the next letter in the alphabet after F, and then it would go on from there to H, etc. Except we haven't gotten there yet. Okay? So we have our shells, we have our subshells. All right, so then with the Pauli exclusion principle, we can figure out then how many electrons that can be in these shells. Okay, so the first part of the exclusion principle tells us there can be 2L plus 1 different values of ML, right? So if L is 0, then there can be 1 ML. And if L is 1, then there can be 3 MLs, 1, 0, and -1. If L is 2, then there can be 5, right? -2, -1, 0, 1, and 2. Because remember, ML goes from -L up to 0 up to L. So the number of MLs there can be and the number in a subshell depends on what the L is. Okay? And then the second part of that is, so then with the spins, that means there can be 2 brackets, 2L plus 1 electrons. Okay, in that particular subshell. So if L is 1, then the bracket is 3. So that means there's 3 different orbitals, and there can be 6 electrons. Okay? So, because there can be 2 electrons for every value of M. That's why there's a 2 in front. So if we go up here then, when L equals 0, the inside the bracket becomes 1. The S subshell, I just want a different color. The S subshell then can have, if L is 0, it can have 2 electrons. When L is 1, this bracket in here becomes 3 times 2, P can have 6. When L is 2, 2 times 2 is 4, plus 1 is 5, times 2, D can have 10. L is 3, so we have 7 inside, times 2, the F could have 14. And then the next one up would be 8 times 9, can have 18. I think I did that right. Okay? And then we would go on from there if we needed them, if we ever found more elements that we would need the next thing up. Okay? So it's from then the Pauli exclusion principle, knowing these different letters, that we can figure out how many electrons can go into each of these shells. So now they were like, okay, but we still need a nicer, a more compact way to write this. So their more compact way to write this is that they use the number for the n. Okay, so the number for the n, they use 1, 2, 3. They do not use, I'm trying to find where it is. There we go. They do not use K, L, or M. They use the number for the n. They use the letter for the L. And then they make the superscript the number of electrons. Okay, oh shoot, now I'm writing on the paper that I wanted. So, instead of writing sodium out like this, then we would say, okay, sodium has 11. The first 2 are in the n equals 1, L equals 0. And so the first 2, it would be 1, L equals 0, we said was S, and there's 2. That's these 2. Then the next 6 are in the n equals 2. Actually, next 2 are in the n equals 2, L equals 0. So it'd be 2, S, 2. Now the next 6 are in the 2P, because L equals 1. So 2P6. And then the last one is in